thank you, Haluk. Okay, so we looked at the discrete series earlier, which is a part of the temporal dual of some groups. If the group is not compact, it's not everything, and sometimes it isn't even a discrete series. So what I want to talk about now is how to go from representations of subgroups to representations of a whole group. And then in the third lecture tomorrow, it'll turn out that by using discrete series representations of subgroups and inducing them up to the big group, we can actually parameterize the whole temporal dual. And the process is parabolic induction, and that's what this lecture is about. I'm going to first talk about induction, unitary induction in general. You can do it just for the groups that we care about, which is the cuspidal parabolic subgroups. But I think saying it in general makes it a bit clearer what's going on. And then, so I'll talk about the groups that we will apply induction to, called cuspidal parabolic subgroups. And at this stage, we really have all the information that we really need from this lecture. And then the last two sections are all about making it a bit more concrete by giving some examples and writing out more explicitly what induction looks like in the case of these parabolic subgroups that we're going to look at. So a very quick recap of this morning. So we saw the temporal representations are the ones that are currently L2 of G. Has discrete series representations, it has a compact Cartan subgroup, and we can classify them. And as I was just saying, we work towards the classification of the temporal representations in the next lecture by this induction procedure and by discussing these groups. Okay, so I'll start with the general setting where G is now not just a semi-simple real D group anymore, just a locally compact topological group. And I'm again picking a setting that's convenient, which is not the most general setting you can do this in, but I'm picking the setting where we have a closed subgroup H, such that there is a compact subgroup K for which this equality is true. So every element of G can be written as an element of K times an element of H. In particular, G mod H is compact. And this will turn out to be true for the parabolic subgroups that we will look at later. Okay. So given a unitary representation of H in some representation space, we want to create a representation of G. And we would like to do it in a way that the induction procedure preserves unitarity. So we want the representation of H to be unitary again. And an extra hope, is that in many cases, the induced representation could be irreducible or close to irreducible if pi was irreducible. And so the second wish is stated in a bit of a more careful way, and it's also much more subtle than the first wish. Unitarity will just follow in general from the construction. But the second question is more delicate, and that will be the topic of the third lecture. There's some geometric intuition behind this. This is in the case where G and H are D groups, so they're manifolds, and G mod H is a manifold. I'm just saying this now just for some intuition of what's happening. What we do is we form this vector bundle over G mod H. This is by definition the Cartesian product, where we divide out the diagonal action by H. And then what you can do is take sections of this and let G act from the left. But that turns out not to give you a unitary representation in general. To make it unitary, you have to twist this bundle by half densities. And in the case where G and H are Lie groups, this is exactly what's happening. Modular questions about infinite dimensional, infinite rank vector bundles. But then you really get a twist by those half densities, which may intuitively make it more plausible that you get something unitary. But in the general group case, I'll mention what the reflection is of this half density twist in the more general case. And then the representation of G in the space of sections, we take square integrable sections in the appropriate sense, will be by the left multiplication on that factor. So that's the intuition. Now the concrete definition. We again use a H measure on G, and has this property as I mentioned in the first lecture. Now we don't assume anymore for now that G is unimodular. So a left invariant H measure is not necessarily right invariant. And that leads to the notion of a modular function, which is the function delta of g with this property. So if you shift the function on the right by an element, it equals the integral times a function. And this is a homomorphism from g to the positive reals. In the case of a B group, this function is the determinant of the adjoint action, absolute value inverse. Then it becomes very explicit. And this will actually be used in the parabolic case later. Now, for the subgroup H, we also pick a Haar measure, and we also have a modular function. And what will turn out to play an important role is this homomorphism. We take the modular functions of g and h, take their square roots, restrict the one on g to h, and then divide this. And this is a homomorphism from g to the positive reals. The space we start with is the space of continuous functions from g to h pi. But we tensor this representation of h by the complex numbers on which h acts by this, this character. And this maps into the positive number, so it's not unitary. But the non-unitarity of this will make the whole construction unitary. So this space, continuous functions from g to this, which are h equivariant in the following sense. If we act from the right by an element of the group h, that means you multiply by this character and apply the inverse of the representation. So f of g here lies in h pi. I mean, tensor with c of chi, which is just the complex number, so it doesn't really matter that much in the space. And then pi of h inverse everything is. So this is the equivariance. And this, without this could be, so without this would be like the sections of the vector bundle I mentioned. But including this factor, in the Lie group case means you're twisting by the half density bundle on G mod H. Okay. Now I want to complete this space into a Hilbert space, so first define an inner product. And what we would like to do is to not integrate over G, but over G mod H. And as I mentioned in our case, G mod H is a compact space, so integrals are more likely to converge there, especially for continuous functions. So how do we concretely integrate over G mod H? You can do this in different ways. The way I'm doing it now is choosing a function, compactly supported function on G, phi, so that this integral equals 1 for every element G. So in a sense, this kind of cancels out integration over H, including this. Then if we have two functions in this space, the inner product, the L2 inner product by definition is the integral over G of this thing. So this is the element-wise inner product in the representation space of phi, but times this function. So the inclusion of the phi means we're really integrating over G mod H. And also the H invariance property of those functions f1 and f2 mean that this is well defined independent of phi. So then we have an inner product on these continuous functions. Of course, now the integral converges because phi is a completely supported continuous function. And this phi exists and can be chosen completely supported because G mod H is compact. Okay, so we take the L2 completion in that product and we call that HG of pi. Then the representation of G in that space, given by something that looks like a left-bracket representation, is the induced representation of pi. So the elements of this are functions on G with an H equivariance property. And we let it act from the left, and that's an induced representation. And this is called unitary induction or normalized induction. And as the name suggests, this turns a unitary representation of H into a unitary representation of G. Writing that out is a matter of getting your integrals right and comparing different measures on the groups. So it's some manipulation of Haar measure. But I just want to give one ingredient to indicate why we need to include this extra, these two modular functions. And that is because for appropriately chosen Haar measures on H and K, the integral of a function over G is the integral over K and H, but we have to include this function. This is because of left versus right integrals and substitutions and those kind of arguments. So this formula is why we need to include this extra character to make it unitary. Okay. So yeah, so this means that in the setting we were looking at, given a unitary representation of H, we can create a unitary representation of the bigger group G. Just as a bit of a sanity check, what happens if H and G are equal? We would like the induction from G to G to be doing nothing to give you back the same representation, and that is true. In the case where H and G are equal, this quotient of modular functions is 1, and a G invariant function is of course determined by its value at the identity element. So evaluation at the identity element gives us an equivariant, a unitary equivalence between the induced space and the space. Here we of course we needed to complete MSL2 although it doesn't really matter because we're integrating over G mod G. So in this case, induction from G to G is doing nothing, as you might hope. There's also relations from if you have a subgroup and a second subgroup, that inducing from the one group to the next and then on to the next gives you the same thing as inducing all the way up. Those kind of natural relations. Okay, this is just a quick summary of unitary induction. I'm going to apply this now to a classification of the discrete series of disconnected groups, because it turns out, we'll see this at the end of this lecture, that we have to use disconnected groups in the classification of temporal representations. Because G may be connected, as we've assumed, we will look at subgroups which can be disconnected, only have finely connected components, but we have to say something about the discrete series of disconnected groups, it turns out. And that can be done in terms of unitary induction, so this is just one application of that. Just as for the classification of the discrete series, the main thing to remember is these things can be classified. Yeah, so the exact procedure won't come back in the lectures. But how does that work? The conditions on the group that we look at, they're a bit delicate. The conditions on G, I stated in the first lecture, are pretty strict, but you still get enough groups to be interesting. There's a class of groups defined by Harris-Chandler, which also allows disconnected groups. I'm going to look at this particular condition over here where the theory works nicely. So we're going to assume that G lies in GLN, so a subgroup of G and C, closed subgroup, closed under conjugate transpose, as we assumed earlier. But we don't assume connected, we only assume finally manipulated components. And we don't assume finite center for now. We do assume that the connected component of the identity has a compact center. And final technical condition, so any subgroup of GL and C lies in GL2 and R. We complexify this. So we complexify G in there, subgroup generated by the complexification of the Lie algebra. And then a technical assumption is that G lies inside this complexification times the centralizer of G in this full general linear group. Okay, so these are just a bunch of technical conditions that we need to make what follows work. So how do we now parameterize the discrete series of a disconnected group of the type I just mentioned? Again, we need a compact Cartan subgroup, T. And we now start with the discrete series representation of the connected components of the identity of G. So we know how to parameterize them, that was the first lecture, and has a parameter lambda. To get all the information about the connected components as well, we need a representation of the center of G, representation chi of the center of G. And the compatibility that we require is that restricted to T intersect with the center, these two characters are the same for compatibility. Because of this condition, we can define a representation of the product. So all the products of these two things. In the following way, so we combine this representation. If you have a group element that equals G naught in G naught and Z in the centralizer, in the center, we define it like this. And then this condition exactly means that this is well-defined and independent of the decomposition here. That gives us a representation of this group, and then we can induce it up from this group to all of G, and that gives us a representation in a discrete series of G. And they all occur in this way, and two of them are equivalent exactly if the characters of the center were equivalent, and the same condition on this on the parameters lambda with this loudness action. Okay. So message here is we can classify the discrete series even for mildly disconnected G, and it's something that we'll use later, and this involves induction. All right. Any questions about this? That was induction from subgroups up to bigger groups, and now I'll talk about the subgroups that will apply this to, possible parabolics. We now go back to the situation of before, where G is a real semi-simple Lie group, so a closed subgroup of G, L, and C, closed uncomplete transpose, and finite simple. What we're going to do is construct cuspidal parabolic subgroups that look like, they're called P, and they decompose as M times A times N, where M is a group which is like G in a sense. It turns out to fall in this more general class that I mentioned when I talked about the discrete series of disconnected groups. So it's not quite the same as G, but it's intuitively the same kind of group. A is a vector group, isomorphic to Rn, and M is nilpotent. The algebra of N is nilpotent. And then we use unitary induction to create representations of G from representations of P. Okay. Now, as in the first lecture, we use a maximal compact subgroup, and for the linear groups that we look at, we can define them in a very concrete way. K is the intersection of G with the unitary group. If G lies in G, L, and C. As I said in the first lecture, the Lie algebra of the unitary group consists of anti-Hermitian matrices. And this space here is the Hermitian matrices. So the anti-Hermitian and the Hermitian matrices together give us the Lie algebra of G. So this is called a Cartan decomposition. The Lie algebra of K plus the Hermitian matrices in the Lie algebra of G together, G is a direct sum. And that leads us to the notion of a theta stable Cartan subgroup. The Cartan subgroup is theta stable if its Lie algebra decomposes in this way. So its component, its intersection with K, direct sum intersection with S, together make up H. And the term theta stable comes from the Cartan involution theta, which in the case of matrix groups is minus conjugate transpose like here. And the relevant thing is conjugacy classes of Cartan subgroups, and every Cartan subgroup turns out to be conjugate to a theta stable Cartan subgroup. So within every conjugacy class, we're going to take a theta stable representative and start from that. Now we'll be using in the product and the construction as well, given by this formula. This is constructed from the Killing form. People have seen this before. Inner product is the minus the real part of the trace of x and then theta y, or theta is this. Okay, so we're starting with a theta stable Cartan subgroup, and we define the space A to be the intersection of H with S. So H decomposes in this way, the compact part and the non-compact part, and this here is our A, we're taking here. And A is really the starting point of the construction of these groups. We start by defining the associated group, which is just the exponent, the exponential of A, because A is a commutative Lie algebra and the exponential map, because it's this group, it's commutative. And the exponential map is now a group isomorphism. So A is isomorphic to A, as I said, which is just some vector space. Then we define the factor n that I mentioned, which is the factor that's supposed to be like G. We take the centralizer of the space A inside the Lie algebra G, so all the elements of G that commute with elements of A. This includes A because A is a Abelian, it's commutative. And we let M, the Lie algebra M, to be the orthogonal complement inside the centralizer of A. Then we can exponentiate this, and we end up in group G. And we take the subgroup generated by all those exponentials, and that's by definition n naught. And the group N is the centralizer of A in K times n naught. We'll see examples later of what this really means. Then M satisfies the assumptions that I mentioned earlier for the discrete series of disconnected groups. In particular, M may be disconnected, even though it has finally many connected components. And what's crucial here is that the M constructed in this way always has discrete series representations. So it always has a compact Cartan subgroup, even if G doesn't. And we will also see this in examples. Now, because M was constructed from the centralizer of A here and here, the elements of M and A commute. So if you just take all the products of M and A, elements of M and A, this is a group, and this is called the Levy factor. Now, I said the parabolic subgroup consists of part M, A, and N. So now we have the parts M and A, and we need to get the part N. And that's defined in terms of restricted roots. They're a bit like roots, but not quite. So for a real valued functional, real linear map from A to R, alpha, we define this analog of root spaces. So again, all the elements of Lie algebra, so that every element of A, if you take the bracket, it's this eigenvalue times X. So again, simultaneous diagonalization of all these adjoint operators bracketing with Y. The difference with roots was we now don't complexify G, and this A is not generally a Cartan subgroup. It's usually not maximal commutative. But we can still make this definition, and we can still define a restricted notion of roots in this way. All the non-zero functionals with this weight space is not zero. The difference with the root, with the actual roots, is that in that case, the root spaces were one-dimensional. Here, these spaces may have higher dimensions than one. Okay, using those restricted roots, we can construct a Lie algebra N, a nilpotent Lie algebra, by picking a positive system again, a bit like the way we chose positive roots when we talked about the discrete series. For the positive roots, they were all the roots that have non-zero positive inner product with some vector, which is basically saying you take all the roots on one side of a hyperplane. We do the same thing now. So we have this is a finite set in the vector space. We pick a hyperplane that doesn't intersect the set, hyperplane through zero that doesn't intersect the set, and we take all the restricted roots on one side of that. So we pick half of the roots and we call them positive. So just like for roots, by the way, every restricted root is either in here or minus the thing is in there. And then we take the direct sum of all the restricted root spaces for the positive restricted roots. And that turns out to be a subalgebra of G. and it's nilpotent. Nilpotent means if you take, there's a fixed n, so that whenever you take a repeated bracket like this, of n elements, you always get 0. And then we let the group n to be the subgroup of G generated by the exponents of n. Turns out that the group NA normalizes n, and that's what makes MAN a group. So this is the kind of group we're looking at. A cuspidal parabolic subgroup of G is a group of this form, MAN, where we constructed M, A, and N as just now. So for N, there was a choice involved. We chose these positive restricted groups. You have to somehow account for that choice. But so the input is theta stable carton, which gave us the A, and the choice of these positive restricted groups. Now, this definition, you can do this much more generally. You can define parabolic subgroups in general, and then the word cuspidal means that the factor M has discrete series representations. The advantage of the way I've written it now is that you automatically get cuspidal parabolic subgroups, and also it's pretty constructive. So if we start with a conjugacy class of Cartan subgroups, then we can construct from that the cuspidal parabolic, so you can really easily list them, construct them. So the general notion of parabolic subgroup is also important, but I need the cuspidal version for these lectures. And some properties. There are finely many conjugacy classes of cuspidal parabolic subgroups. We have this property here that every element of G can be written as an element of K times an element of P, so that there was an assumption in the construction of induced representations. And also, these group have trivial intersections, so this is a diffeomorphism. N times A times N onto P is a diffeomorphism. So you can decompose every element of P uniquely as N times A times N. Okay, so for now, I've basically stated all the theory we need. Are there any questions so far before I move on to some examples and to a concrete form of the of induction for cuspidal parabolics? Okay. Now, examples are very important in representation theory because you can see the definition, but it's really helpful to see what they say in concrete examples. So the first example is if you have a compact Cartan subgroup. So that means if G has a compact Cartan, then it means it has discrete series representations. So what's the cuspidal parabolic associated with a compact Cartan? Well, in that case, H lies inside K. So the intersection with S is 0. So the A component is just 0. So the exponent of that is just a trivial group. Now, the centralizer of A is all of the Lie algebra because A is 0. And the orthogonal complement to A, which is 0, is all of G. So the Lie algebra M is all of the Lie algebra G. Now we take the subgroup generated by X of M, which is in this case X of G. And the subgroup generated by X of G is the connected component of the identity in G. And we've assumed G is connected, so this is all of G. So M0 is already all of G, and if you then also add Zk of A, centralizer of A in K, we still get all of G. So M is now all of G, and the N component is also trivial, just like the A component, because A is the 0 space, and there are no restricted groups. We can't add any restricted group spaces together. So, moral of the story, for a compact Cartan subgroup, A and N are trivial, and M is all of G. And in other words, G is a cuspidal parabolic subgroup of itself, if and only if it has discrete series representations, i.e., if and only if it has a compact Cartan subgroup. Now, SL2R are a running example. First, look at the compact Cartan subgroup SO2 of SL2R. And as I said on the previous slide, if you start with a compact Cartan subgroup, the cuspal parabolic is SL2R, is the whole group. So this is M, and A is trivial, and N is trivial. So this just follows from the general case for compact Cartans. So now we look at the non-compact Cartan subgroup of SL2R, this one, the diagonal Cartan subgroup. The Lie algebra is then spanned by this matrix and completely lies inside. And so remember, S is the Hermitian matrices inside G. And this is a Hermitian matrix. And so yeah, the Lie algebra is generated by a Hermitian matrix and lies completely inside S component. So A is now all of our Cartan. So it's the opposite case of a compact Cartan. There, everything lies inside the compact part, and now everything lies inside the non-compact part. The exponential A is now looks a lot like H, except that we now only take positive numbers R here. So this group here is disconnected, has positive and negative X, but this A is always connected. So it's 1/2 of it's the connected component of identity of H. Okay, now what about the N part? The centralizer of A in G is now just A, and the orthogonal complement of A is therefore just 0, so M is just 0, which means that M naught is trivial because it's generated by the exponentials of elements in M here. But M is not quite trivial because we still have to add the centralizer of A in K. And that's all the elements of K, of SO2, sorry, now K is also SO2, that commute with all the elements of A. In other words, that commute with this matrix. And the identity and minus identity both commute with this matrix, and no other elements of SO2 commute with this matrix. It's something about matrix computation. So M, in the end, has two elements, plus and minus identity. And this is a disconnected group. It's also finite, so it has discrete series representations because every representation is a discrete series because it's a compact group. So this already shows that disconnected groups pop up naturally in this context. Okay, so what does the parabolic look like? So we had our A is now the diagonal matrices with positive elements, and M is plus minus identity. Now what's our N? Okay. So our space A was spanned by this matrix. And we need to look at the restricted roots to form N. Now it turns out that the restricted roots are plus and minus alpha. Well, alpha is the element that pairs to 2 with this Y2. Then well, this is basically something we saw in the root case earlier, in complex case. But the restricted root space for alpha is spanned by this matrix, and the restricted root space for minus alpha is spanned by this matrix. To define N, we pick a positive set of restricted roots, so we can pick either alpha or minus alpha. So we pick alpha now. Then N is the direct sum of all the positive restricted root spaces, which is now this. And if we take the exponentials of the elements in here, we get this. The exponential map now just has 2 terms because the matrices are nilpotent. This is now our N. We could have chosen this one and the X would have been here. So what does P look like? P is all products M, A, N. So M was these elements, A was these ones, N was these ones. And if you multiply them all together, what you get is all matrices of this form. So basically the upper triangular matrices in SL2R. And that's so the cuspal parabolic associated to the non-compact Cartan of SL2R. Okay. Now, in the case of SL2R, the two cartons are either completely compact or completely non-compact. So to give an example of what can happen in general, I want to look at SL3R, because more things show up here than for SL2R. For SL3R, first let's look at the diagonal carton. You again can take the, if you start with the carton of the diagonal elements in SL3R, by doing a similar computation as before, I'm giving a bit less detail here, but it turns out that the A factor is again the diagonal matrices, but now only with positive entries. The M factor, again the Lie algebra M is again 0, because A is some centralizer in G. But Zk of A are all elements in K, which is now SO3, that commute with matrices of this form. And this turns out to be a finite group again, epsilon 1, epsilon 2, and then their product, where they are both plus or minus 1. So we have a 4-element group here. And now if you choose some positive restricted roots, what you get is a upper triangular subgroup of SL3R. Just like here we got the upper triangular matrices in SL2R. If you start with the completely non-compact carton, you get the upper triangular matrices in SL3R. And again, I'm not giving all the arguments here. They're analogous to SL2R, and actually this also applies to SLNR more generally for the diagonal carton. Now, what's a bit more interesting is this carton, which is a mix of a mix of compact and non-compact parts. So this carton subgroup here, it contains the circle. There's like SO2 matrices in the top left, but also a factor X. And these matrices all lie in SL3R, and it's a maximal abelian subgroup, and this turns out to be a carton. Now, the Lie algebra of H is spanned by these two matrices, this generator of this SO2, and this one. This one is anti-Hermitian, and so it lies in K. This one is Hermitian, so it lies in S. So now we have a part in K and a part in S, which makes this a bit more of an interesting example. Okay, so A is the part inside S, which is spanned by this matrix. And if we take the exponents of this, we get all these matrices. Now, what's the centralizer? The centralizer of A in G, it consists of A itself and these 3 by 3 matrices, where the X in the top left is a matrix in the Lie algebra SL2R, so 2 by 2 matrix with trace 0. Now we take the orthogonal complement of A, which is now this part, which is our Lie algebra M. So M, the Lie algebra is SL2R, embedded into SL3R. And M naught is all the exponentials of all these Lie algebra elements, which is now SL2R times 1, the 1 coming from there. Okay, so M naught is SL2R. Now we have to also add the centralizer of A and K. Now K is SO3, and the centralizer of A in SO3, so A was generated by all the matrices in SO3 that commute with this matrix. That is the matrices of this form. So an orthogonal matrix, 2 by 2 matrix in the top left. And then to give a determinant 1, we have to put the inverse determinant here, which is plus minus 1. So then the group M consists of all the products of elements on the centralizer times these matrices in M naught, which was SL2R. And then you get the matrices of this form, where now G is in a slightly big group in SL2R. G is in SL2R plus minus, which means it has determinant plus or minus, which is contains SL2R, but it's slightly bigger. So this is SL2R. And then we add in the determinant for, you can leave out the minus 1 because it's plus minus 1 anyway. But this then lies in SL3R. And again, we see it, M is disconnected because it has these components with determinant +1 and determinant -1. You could imagine, because we saw that SL2R has discrete series representations, so this group, which is not like it, also has discrete series representations. So this example shows in a slightly more interesting way what can go on with this group M. It's like the group G we consider. It's like SL2R, which we know has a discrete series representation, except it's a little bit different and it may be disconnected. Okay, now the group N, to make it complete, A was again generated by this matrix. Now A is one-dimensional again, and that means that the restricted roots, there's two of them. Alpha here is the element that pairs to 2 with this matrix. The root spaces, the restricted roots are two-dimensional. As I said, they can be higher dimensional than 1. For alpha, it's these matrices, and for minus alpha, it's these matrices. We make a choice. We choose alpha to be positive. Then N is this, and if we take all the exponents of all the matrices, we get this group. So that's N in this case. And when we put them all together, M times A times N into our P. So our elements of M look like this, where G was inside this group SL2R plus minus. A were these matrices, and N were these matrices. And if you combine them all together, what you get is the matrices that look like this inside SL3R. So all the matrices for which these two entries are 0. And I've drawn the lines here to show that what's happening is that you get blocks on the diagonal. You have a 2 by 2 block here, 1 by 1 block here, and we fill up the top right in the matrix. And that's in a more general case for SLNR. You also get blocks on the diagonal, and then you fill up the top right. That's what the parabolics you get. Okay, so that's a slightly more advanced example than SL2R, but it's again still just multiplying matrices. Okay. I think this is the last example, SLNC. I said a special thing about complex groups is that they all have one conjugacy class of cartons. So we now pick the diagonal carton subgroup, which looks like this, inside SLNC. And then we do similar computations to what we saw earlier. And then it turns out that group A consists of the diagonal matrices with positive entries in determinant 1. M is like this, n minus 1 copies of the circle. And N can now be chosen by a choice of positive restricted roots to be the upper triangular matrices again. And then P looks like the upper triangular group inside SL and C. We now saw that M, so M can be non-compact in general. We saw that it can be SL2R plus minus for SL3R, but now it's a torus, which is particularly easy. And that's true in general for complex groups. The M part is a torus with only one conjugacy class of costal parabolics. So in the complex part, everything is a bit easier. Okay. So those were some examples of cuspidal parabolic subgroups. And the last part of the talk is what unitary induction from those groups looks like explicitly. Okay. So the representations that we'll be inducing look like this. We start with the cuspidal parabolic MAN. Now, we won't use representations of N. N is there to fill up the space. We take a unitary representation sigma of M hat, unitary representation sigma of M, and unitary representation mu of A hat. And the point is we can classify both these things. So A hat is isomorphic to Rn, or you can say it's A star or something. It's a vector space, and we know the representation of a vector space. We know the representation of Rn, they're parameterized by Rn again. And this part, of course, we can't generally classify all the unitary representations, but it will turn out we're going to use the discrete series of them. But now, for a general unitary representation sigma, we can define a representation of P by this formula. So we decompose any element of P as MAN, which we can do in a unique way. We take sigma of M, mu of A. This is a scalar, so it also acts on the representation space of sigma. And we do nothing with the N component. Now then there is something to check that this is actually a homomorphism. And that's the case because MA normalizes and it follows from a short combination. This is homomorphism for that reason. So these are the representations we're going to be inducing. And they will look like this. So we take this representation of P, and then we induce that from P to G. And we hope to construct the template representations in this way. And because we can classify these, and there are finally many conjugacy classes of Castle parabolics, that means we can classify all the template representations of G. There's one term I want to mention, which is the principal series. The principal series is simply these representations for the smallest possible P. So for example, for SL2R, we found two Castle parabolics, the whole group SL2R and the upper triangular group. So the upper triangular group is the smallest one, and the ones we induce up from there are the principal series. And for the principal series, for the smallest possible Castle parabolic, the factor M is a compact group, so this becomes particularly easy to classify like these. So in the case of SL2R, M is just a two-element group. Okay, in the rest of the lecture, I want to write down 3 explicit pictures of a unitarily induced representation like this. And this involves another row element. Row, as I said, is always half the sum of positive roots. In this case, restricted roots. So we take the positive system sigma plus that we use to define N. The Lie algebra N is a sum of the positive restricted root spaces. And then we take rho to be half the sum of those positive roots, where we count them with multiplicity. We saw for SL2R that the dimension of G alpha may be bigger than 1. We multiply by the dimension. Now, rho lies inside a linear functional on A. There is no integrality condition here because the exponential of A is 0, or you say A is a vector space group. So every element of A star gives us a homomorphism e to the rho from A to 0 infinity. By this formula. The exponential is now injective, so this is bijective. Okay. Now this is this is called the induced picture. This is one explicit way of writing down the induced representation for a parabolic subgroup. Right. So we start with a representation of M and a representation of A. And now this induced representation space, this was by definition the construction from induced representations. We now get this by looking at all the functions f from G to H sigma, where you have this transformation behavior. So for a group element G and G, then MAM in a parabolic, we have this factor involving rho. This is the concrete representation of A, and then this. And then the inner product of two elements, we can compute that by integrating over K. So restricting them to K and integrating that. The claim is that this is what you get from the construction the general construction that I described earlier. Just some points from the proof. This quotient of modular functions is now this factor e to the minus rho A. That's because the G is unimodular, so the modular function for G is just 1. P is not unimodular, but the modular function for P is given by this factor in big square roots. So the equivariance condition on F in the definition of unitary induction now becomes, this is the definition, and it just becomes this what we saw on the previous slide. This is just a direct translation of definition to this kind of group and this kind of representation. And so the fact that the integral is given by the integral over, so the inner product, the inner product, which was in a sense an integral over G mod H, now becomes the integral over K via this kind of relation that I mentioned earlier, which was used in the proof that unitary induction gives you a unitary representation. So a computation involving this shows that the inner products are also the same. Okay, now what I just said is really quite literally applying the definition. There are two other pictures which are convenient in different situations, and those are based on the fact that they both come from restricting to certain subgroups of G. First of all, by restricting to K, we get the compact picture. And this is true because G equals Kp, so if you have a function on G with specified transformation behavior in P, that means that if you restrict to K, that's an injective map. And this is the result of that restriction. The space then becomes a space of functions from K into the representation space of sigma. Transformation behavior is now a bit simpler, which is one advantage of using this picture. The inner product is the same, integration over K. But the advantage of this picture is that the representation space is independent of mu. So mu is a continuous parameter, and the sigma is a discrete parameter. So maybe sometimes you want to look at these continuous parts of your temporal dual, and it's convenient sometimes to use the same representation space on this whole continuous family. And this compact picture allows you to do this because the mu drops out. The representation looks a bit different. The disadvantages for the first picture, the representation is just multiplying by the lift. Now the representation is a bit more complicated. If you have a group element G and a function f of this type, you evaluate it at a group element K. It looks like this, but where A, M, and K are now defined by this relation. So it's a bit more complicated. You take G inverse, because you know, F is only a function on K, so you have to get something inside K to evaluate F at. But what you do is you take the element K prime where you want to evaluate it, and then you decompose G inverse K prime in this way, which is possible because G is K and AM. It's not unique. There can be factors between K and M, transferring back and forth, but it turns out not to influence things. And you need to know this K and this A to define this action, so that's a little bit less explicit. But this turns out to be equivalent to the image representation as well. And then the last picture is a non-compact picture, where the subgroup is this. So it's in a sense the opposite n. So you have different n's for different choices of positive restricted roots. This is a different one which explicitly looks like this. You take all the conjugate transpose inverses of elements of n. They form an opposite n. And restricting functions from G to this n bar is injective on this space because n bar times n times a times n is not quite all of G, but it's open dense in G. So if you have a continuous function, there's restriction to this. So if you have something here, you restrict it to here because of the transformation behavior here. Yeah, this tells you what happens in this direction. And because this whole thing is open dense, this is an injective restriction map, and the image is the non-compact picture, where the advantage is that the space is relatively simple. So there's no transformation behavior in the definition of this representation space. It's just an L2 space on this group n bar, where the measure is a H measure on n bar times a weight function. And the weight function is this expression over here. So the advantage of a non-compact picture is the space is relatively simple, and also it's smaller, right? Just like in the compact picture, if you have functions on G, it's always more complicated to handle than functions on K or functions on the small group N bar. Okay, I started a bit later, so I probably have time for just the example here. So the principal series of SL2R means induced representations from the minimal parabolic subgroup, the upper triangular parabolic subgroup of SL2R, where M was plus minus 1, A was this, N was this, and now this N bar is the low triangular difference. And then the group M has two representations, two induced representations, namely the trivial representation and the non-trivial representation, both in the complex numbers. We call the trivial one sigma plus and the non-trivial one sigma minus. And A is isomorphic to R, and we take a representation mu of A, which is parameterized by a real number. Okay. Now, for sigma plus, these induced representations are called the spherical principal series of SL2R. Spherical means if you restrict to a maximal compact, the trivial representation of the maximal compact occurs with positive multiplicity. Explicitly, you can describe the representation space now as just L2R, on which a group element from SL2R, written like this, acts in this way. So this is an explicit form of those principal series representations. For sigma minus, you get the non-spherical principal series, again the representation space L2 of R, and the action is the same as previously, except we have the extra sign here. So this is just an explicit form of what this looks like for SL2R. Okay, well, quickly the SL2C. For SL2C, we have the Castral parabolic, again, upper triangular matrices, where M is the circle group, R is this, and N is this. Now, the principal series representation of SL2C is now in L2 of C, given by a similar representation as before, except this factor now is new, because now M is a bigger group and there's more representation parameterized by an integer, and this is this integer, just to indicate what the representations look like. Okay, so now we've seen how to induce representations up to a bigger group, and we've seen what Castral parabolics are. And tomorrow, in the last lecture, I will combine all those things together with things about the discrete series to classify almost all kinds of representations, and particularly look at which ones are equivalent and when they're irreducible. All right, that's it for now.
Thank you, Peter.